Now, the next theorem, in any metric space, in any metric space, say in any metric space, say m comma rho, the sets m and pi are both closed sets. So this is a very simple one, so not like a proof. So a set, this M contain all its points. M is a full set. M is the full set. This is not a subset. So entire set is there. We consider this M. All points are inside this M. So definitely limit points also must be inside it. Okay. So that's why it's obvious that the set M, the full space, metric space M is closed, and empty set is closed because it has no elements. If the elements are there, then only we can discuss about whether the limit point exists or not. It has no elements, so it's closed by default. So like this we can write the proof here. It is obvious that the metric space M, which contains all its points, also should contain its limit points. Hence M is closed, and the empty set, say pi, has no elements in it. And there is no need of discussing of whether limit points exist or not. So empty set has no elements in it, and hence it contains all its limit points, and it is closed by default, and it is closed by default. Or I can use the same wordings as per the author of this reference text. Empty set has no elements in it and is closed. And for that, what the author says is the empty set has no elements in it, and hence contains all its limit points. And hence it is closed. So this is a very simple thing. This is like a statement, we can write it. So you must know that already we proved that the empty set and the full set are open sets. So here now we proved both of them are closed sets as well. Now the next theorem, in the open sets section, we proved if we have a finite or countable collection of open sets G1, G2, G3, then if we union all of them, that also is open. The countable collection of open sets is there. Then if you union them, then the resulting set is also open. But only intersection of finite number of open sets is open. Now the same thing is we are going to consider for closed set also. But the thing is only finite union and arbitrary intersection of closed sets is closed. So that's what we are going to prove here. So now, if F1 and F2 if F1 and F2 are closed subsets of the metric space M, then F1 union F2 is also closed. We have to prove this. Now, so that is what we are going to prove, that is F1 union F2, the finite union. The closure of this must be equals to what? F1 union. This is what we have to prove it now. Because we have to show that F1 union F2, the set is closed. So the closure must be equal to the given set. That is, it contains all its limit points. So, but already we know that always the given set is a subset of its closure. It's required to show that F1 union F2 closure must be equals to the set. But F1 union F2 is always a subset of its closure. This is true for any set, and hence it is required to show that we have to prove only that F1 union F2, the closure must be a subset of F1 union. For that purpose, we are going to take one element from this F1 union F2 whole bar. Let us assume one element belonging to F1 union F2, the closure. So the meaning is, so X is belonging to the closure of F1 union F2. So what is the meaning of that is, X is the limit point of F1 union F2. What is the definition of limit point? There exists a sequence of points in the given set that converges to that X. So, and so there exists a sequence, there is a sequence of points. There exists a sequence of points, say Xn, of this set F1 union F2 converging to this X. That's the meaning of X is belonging to the closure of F1 union F2. So now what happens now, you see, you have to think like this. This is F1 and suppose this is F2. And now this sequence belongs to what? X1 union X2. So the sequence can be either completely in F1 here, the sequence, or completely in F2, or it can run between F1 and anything is possible. That sequence, that Xn sequence we are telling. So that's what we are going to think now. But the sequence Xn must have a subsequence, consisting wholly of points in F1 or a subsequence consisting of points in F2. See, that's what. That sequence may run from F1 to F2. You think like this. Suppose it runs between F1 completely inside F1, that we will not consider. We will consider that there is a big sequence that runs between F1 and F2. So there exists some part of the sequence, a subsequence, that is called a subsequence, that is entirely in F1, and some part of the sequence, that is a subsequence, that is completely in F2. That's what we have written here. So Xn must have a subsequence consisting of wholly points in F1, or anything can happen. Can be completely inside F2, but some points are in F1. So that's why we written a subsequence of points fully in F1, or consisting of subsequence consisting wholly points in F2. Since any subsequence, we have already studied sequences, any subsequence converges to the same limit as the original sequence. So we have proved that, just now shown that this sequence converges to a limit x. So any subsequence also must converge to the same limit. Since that's what we are going to express here. Since any subsequence of this sequence Xn must converge to X. So both of these subsequences we have listed above must converge to the same X. Okay. Since any subsequence of Xn must converge to X, this shows that this X belongs to F1 bar, or this X belongs to F2 bar. See, suppose you think this is F1 set, this is F2. So now this is a sequence you think suppose this is a sequence. It goes on like this. There's some points here and here, both it spreads in X1 also. So this is the sequence, subsequence in completely in F2, and this is the subsequence completely in F1. And the original sequence, the full sequence, we have seen that it is converging to what? X. Therefore, as per the sequences chapter, the subsequences of any sequence also, this also must converge to X. So this subsequence also must converge to X. So now, what happens is, this part which is inside, completely inside F1 is a sequence. Subsequence is also a sequence converging to this X. And this is another subsequence inside F1 converging to X. So what you can tell about X here for this set F1? So X is the limit point of F1, and here the same X is the limit point of F2. That is why X is element of the closure of F1 and X is element of the closure of F2. That's what we have written here. Okay, we cannot visualize it, just I try to view it. You can understand this, why we written X is element of F1. That is what it is written R. Therefore, X is element of F1 closure union F2 closure. But F1 and F2 are closed sets. Therefore, F1 must be equal to the closure and F2 must be equal to its closure. Therefore, from here, X is an element of F1 union F2. Okay. Now, initially what we had, we took an element X from this set. Now, finally we proved that it belongs to F1 union F2. Therefore, F1 union F2, the whole closure is a subset of F1 union F2. Therefore, already the other way is true. So therefore, we can show that F1 union F2 closure is nothing but F1 union, that is the union of closed sets is also closed. If F1 and F2 are closed, then the union of closed set is also closed. That is the meaning of this thing. So you have to understand this part, the sequence part, now why it splits. We are considering two subsequences. Okay. So now you come across the question. So in open sets, what we proved is countable collection of open sets we have taken. That is infinite number of collections, but it should be countable. If you union them, then the resulting set is also open. But here, only finite union of closed sets is closed. We cannot take infinite collection of open closed sets and try to make it as a union. You will get a closed set. That is not true. That is not true always. So for this one, we are going to give an example. So now, note. So this is an example. Now consider the intervals, closed intervals, something like this: 1 by n, 1 minus 1 by n. So there are many infinite collection, the countable collection of open intervals. What are they? I1, I2, I3, like this countable collection. It's not finite, infinite, but countable. So now you can just plot it and see what is happening to this set of intervals. So what is I1? You can just see what is I1. 1, I1. So this is not possible. Okay. So it should be 1. So this is a singleton element, singleton set 1. Singleton set, that is I. What is I2? You can see I2 equals to 1 by 2, 1 minus 1 by 2, that is 1 by 2. This is also a singleton set. Yes, 1 by 2. So what is I3? We can see 1 by 3, 1 minus 1 by 3. So that is nothing but 1 by 3, 2 by 3. Something around this. 2 by 3 somewhere here. And 1 by 3 somewhere here. This interval, set of all points, this is I3. So what is happening to I4? Just you can guess it. 1 by 4, 1 minus 1 by 4. There is nothing but 1 by 4, 3 by 4. See, 1 by 4 is here. And 3 by 4 is somewhere here. This is I4. So now you can guess what would be I5. Some other this point and it will come here. So somewhere like this. So now this left hand point of each interval is approaching what? Is approaching, coming close to 0. And what about the right hand part of each interval? It is coming very close to what? 1. Very close to 1. You can see the right hand part comes very close to 1. The left hand part goes to 0. This is what happens. Now if you union all these intervals, what you can guess by seeing this way, definitely this 1 as well as 0, sorry, this is 0. Definitely the 0 and 1 will not be approached because we are going to union all these elements. Both of them will come very close to this endpoint will come very close to 0, this endpoint will come very close to 1. So what happens is the union of all these intervals n equals to 1 to infinity, this is equals to 0 will not be considered, 0 and 1. But this is not a closed set. Not closed. Why it is not closed? Because the 0 is not included in the set, but I can find one sequence 1 by n that is coming very close to 0. There is a sequence approaching 0, but 0 is a limit point of this set, but it's not inside the set. So this is not a closed set. And here 1 is included, so that's why we put this one, this union. But 0 is not included. If you can see, by visualizing, you can see the left hand part will come very close by. So from this example, what we can conclude is, and this example actually they can start with 2 to infinity also. So 3 to infinity. Yes, maybe 2 to infinity will be correct. If we use it here, 2 to infinity, so this one we can avoid. Because if you put n equals to 1, it comes like 1 comma 1 minus 1 0, 1 comma 0. So you can just put it here 2 to infinity. But anyway, this is a countable collection of closed sets. Yeah? Countable collection of closed sets. But this author is using this I1, so that is not a problem. You can use it. Okay. So now this completes the explanation for why the countable collection of union of closed set is not closed. For this example. This example I show that it's not true always. Only finite number of closed sets you take it and union, then only it is closed. Now the other thing is intersection. There in open sets, finite number of intersections of open sets is only open. But here countable collection of open sets, closed sets you take and intersect, it will be closed. That is the next thing. If f script f is any family of closed subsets of a metric space M, then the intersection of all the elements of this family is also closed. So now to prove that this set is closed, so what we are going to prove is intersection of F, the closure of this. So this is what we are going to prove. Is equals to intersection of F. Same thing. Always this is contains this. Now we are going to take one element from this set and prove that this element belongs to this. So now let X belongs to intersection of F, closure, the F. Okay. So then X is the limit point of this set. Then we use the theorem. What is the theorem? If X is a limit point, then every open ball about that X contains a point of the given set. Then any open ball, say B, or with center at X, radius is something R, contains a point Y which belongs to intersection of F, where F is element of vector. Thus, for now Y belongs to intersection of all these closed sets. So what happens? Y belongs to all the sets in that collection. So thus for any F in this collection, this family, the open ball B, because this open ball contains a point of Y in this, so same thing I can extend. This open ball contains a point Y in every collection of this family. So thus for any F in F, the open ball contains a point of F that's for any F in F, the open ball, say Y. So not say, it should be Y1. Hence this X, again this hence, no, this, I can use that implied symbol. Again that theorem I am using it, the theorem which I highlighted in the previous proof, the same theorem. So by using that theorem, now we restrict to F. Each F is a closed set. So contains a point of F, namely Y, which implies that X is an element of the closure of F, but the closure of F is nothing but F. Okay? Because each F is a closed set. This theorem is very, very important. This theorem, what I use now. So both ways we can use it. Thus, now Y is belonging, this open ball contains a point Y which is in every closed set F. So that one I have explained here. Thus, for any closed set we take in this family, this open ball contains a point of F. What is that point? Namely Y. So what you can tell about the point X as per the theorem? X is the limit point of the set F. That is, X is element of the closure of F, which is equal to F. But closure of because F is a closed set, this closure must be equal to the given set F. Thus, this is true for any closed set in that family. Thus, X lies in every closed set in this family. If it lies in every closed set in this family, then so X must be belonging to the intersection of all the closed sets. So what we started in the beginning, X belongs to the closure of this intersection. Now we prove that X belongs to this. See, actually this is what we have to prove. Therefore, intersection of F, where F is an element of this family, its closure is a subset of intersection of F, where each F belongs to. Therefore, intersection of F, where F is element of the family, is a closed set. This completes it. So again we are using the same theorem. So that theorem is very, very important Without the theorem, these theorems we cannot prove it. So X is element of closure we taken. Then here also we use the same theorem. Instead of this I can use implies. This implies any open ball B contains a point y in, at least one point y in this intersection. So thus for any f, because of the intersection property we are explaining this. Thus for any f in the open ball, the property of intersection we are linking with this theorem now. So thus for any f in family, the open ball times the point of f, namely again here also we use that theorem. So how many times we use that theorem? So thus for each f, that y belongs to each of this f. For each f, this open ball contains the point of y of that f. So again by that theorem, no, this is a theorem we have not used that theorem. Sorry. So thus we are using the property of intersection. From this we are writing here using the property of intersections. If the y belongs to intersection of the big sets, it is belonging to each and every set. For that purpose, thus for any f in the open ball, the same thing we are writing in different group. Open ball contains a point of f, namely we are talking about an individual f. Okay? So then now we apply the theorem here. Why we get this one? It is by that theorem we got this X is element of closure. Okay, so this completes the proof of this set. Proof of this theorem.